on the stage.
Hello, hello, hello. Is it too loud? That's good. All right. Well, thank you for everyone who's attending. The introduction and the name of the presentation is actually a bit wrong. Phazebreak Coatings is an American company that manufacture different types of coatings, and one of the products in our portfolio is an Icephobic coating, which is designed for turbine blades. I'm freezing today, but my palms are sweating. I will be speaking about the similar situation that might be happening in turbines in cold climates, and we are trying to understand the synergy between active heating systems, which are heating units, and passive anti-icing coatings. So, a brief introduction. I'm sure most of the folks listening are very well aware of the impact that icing has on turbine blades. It affects the energy production. It also affects the structural loading of the blades. So large ice buildup can be very crucial to long-term blade health, which I will also speak a bit more today. And also operational availability. So icing is always considered just a thermal problem, but it's not. It involves aerodynamics, the materials, the blade surface, and structural dynamics. So they all come together to solve icing. So why this adhered ice matters and why it's so important to get rid of it. Aerodynamic degradation, mass imbalance, and increased loads. From a lot of projects we've done in the past, we're actually seeing that because of a hydrophobic and icephobic surface, especially on larger, newer blades, we're seeing less micro damages from internal inspections in the springtime, which has to do with the fact we are able to mitigate large ice buildup. Now a bit about icephobic coatings. I think there's been a bit of a misconception in the past about what the coating really does. This is our fourth Winterwind, and we're constantly learning and developing and advancing. And we have to say that the coating doesn't turn winter into a summer. On a coated blade, in most severe icing conditions, ice still might be building up. However, they reduce the anchoring points for ice where it can bond, and at certain time and certain level of ice, you need less force for it to shed. So we're reducing surface energy, we are lowering the ice adhesion and real contact area, and in a practical term, we're making the surface slippery and preventing ice to adhere. And that's also when ice might shed, you're not chipping off pieces of the blade because the ice can be so huge. And there's also been a misconception that we're going against the heating units, where in reality we're not. The heating approach works very well and is a very well-designed and sophisticated system that has been developed for years. Just some key facts. So it raises the blade's internal temperature, it's weakening the ice and helping to enable operation for turbine. It's a proven technology. It's offered by the turbine manufacturers. There's also retrofit systems, but that's the system that's fighting the thermal side of icing. Now, this is to clarify that I'm not saying these systems are bad, but of course everything has some natural limitations of it. Same as coatings, heating units also have some boundaries. So usually heating is localized. We are not heating up the full blade. Mostly heating is focused on the leading edge, and it still can be localized, sometimes more to the tip, more to the root, and even if they say that it's not localized, it still might happen. The temperature is also not uniform. That also has to do with how much blade is growing on different areas of the leading edge. And a major problem that we're seeing in a lot of our projects, even though leading edge might be hot and some of ice starts to melt. There are refreezing behaviors that ice might refreeze on the trailing edge or on other areas that these loads are more crucial to the blade's integrity than just the ice on the leading edge. So these are some of the facts. And now it's good to acknowledge that both technologies have been significantly improved year by year. Just as isophobic coatings are continuously developed to reduce ice adhesion, to increase the water contact angle and have it more durable, the heating systems are also advanced. We are seeing more smarter control logic systems with different analysis of icing events. We're trying to reduce the energy consumption of these heating units and improving the integration to the blade where the internal doesn't become so complex where nobody wants to deal with that. So these fields are both actively evolving. So they're very complementary. Although these are two mechanisms, they're fighting one outcome that is unified. Heating weakens the ice, initiates debonding, but the surface is actually determining what happens when ice needs to shed. So if we're heating up the leading edge, we're reducing the ice strength and interfacial temperature from the inside, but coating is acting from the outside. And if we can make the surface efficient for ice to shed at the moment when the temperature reaches, we're achieving the best possible result to shed the ice in a healthy way for the blade. We are reducing the potential refreezing behavior, and we are essentially trying to get the turbine back online running quicker. And the shedding time matters because just like I mentioned previously, if ice grows too big, it's very crucial for different loads of the blade, whether this is flex or other physics mechanisms. It can really hurt the blade in the long term. So yeah, this is kind of the most important thing. And so from the research side, we are continuously trying to develop and see more things. We are coating first heated blades that are done by manufacturer level, and we think this is the future for research on this combination that complements each other, how heating plus surface technology can maximize the efficiency for wind turbines in the winter. We're reducing energy output. You need to heat your blade less because the surface will be weak quicker for ice to shed, and we're improving predictability of an icing event. So with heating or without, your blade surface always matters. Active heating to weaken ice, but the surface will still need to be isophobic for ice to shed quicker. If this approach is taken at the right time, not being done up tower, it's a very efficient solution. As of why not to take this proactive decision to make the blade's surface isophobic and hydrophobic before it's too late. So whether you have heating or not, this is still a good solution to prevent icing and damages. We're seeing good results also on a lot of smaller blades with just the isophobic coating, as well as on some newer Vestas turbines. So whether you have heating or not, the solution of coating is very valuable. So in conclusion, these are two different technologies, but they're fighting the same problem. I think the industry have been a bit too divided to come together to evaluate these solutions together. We have a first manufacturer that is doing it this way with great results, and we're hoping this year will bring more people looking towards this way to really optimize the blade health in the long term and have ice shedding be more predictable. Thank you.
Thank you, Matiss. So I have a practical question for you. if one is interested in evaluating what this solution of coating plus heating, what would be the right time to do it?
So the right time is to do it when the blade is on the ground. On a real scale, the cost for a coating in comparison to a heating unit is very inexpensive. So we do a lot of projects when the blade is on the ground at some point of the logistics steps, whether it's at the factory or at the port, or during, let's say, blade bearing change when the blade gets lowered. Because it can get quite costly if you do it up tower. So the earlier you address this potential upgrade, the better, the more efficient it will be. And then treating this together with repair steps moving down the road.
Okay. And one last question. Is it an additional weight that's added to the blade if it's coated fully? Or is it not? Or how much does it weigh?
So it's about 8 grams per square meter, so it's very insignificant. According to blade engineers from a manufacturer, I cannot disclose, but you can ask me later. It doesn't have any effects on the blade's aerodynamics or anything to do with it. It doesn't have any negative effects, it just has positive effects.
That's very crucial.
Yeah.
Okay, interesting. Thank you so much for your presentation and for the information you've shared with us. And just as with Vera's poster, you can also see Matiss' poster in the middle here on the screens if you're interested. And this was the end of the first process session for today, so thank you very much.